Welcome to our comprehensive lecture on the geography of India, focusing specifically on soils. Today, we're going to dive deep into the very foundation of our agriculture and ecosystems. Let's start with the basics. What exactly is soil? It is the thin top layer on the Earth's crust, made up of rock particles mixed with organic matter. Soil isn't just dirt, it's a complex natural resource that sustains life by supporting plant growth, regulating water flow, and providing a habitat for numerous organisms. The scientific study of soils in their natural environment is called pedology, while pedogenesis refers to the natural process of soil formation, which includes weathering, leaching, and calcification. Soils are fundamentally classified based on the proportion of particles of various sizes. If a soil has a greater proportion of big particles, we call it sandy soil. Because water drains quickly through the large spaces, sandy soils tend to be light in color, well aerated, and dry. On the other hand, if the proportion of fine particles is higher, it's clayey soil. Clay particles pack tightly together, leaving little space for air, but they hold a lot of water, making the soil heavy. Finally, if the amount of large and fine particles is about the same, the soil is called loamy. Why is loam considered the ideal topsoil for growing plants? It's because loamy soil is a perfectly balanced mixture of sand, clay, and a third type of particle called silt. Silt typically occurs as a deposit in riverbeds, and its particle size falls right between sand and clay. Importantly, loamy soil also contains humus, which is decomposed organic matter. This combination gives it the exact right water-holding capacity required for optimal plant growth. In India, we can broadly divide soils into two geographical categories, peninsular and extrapeninsular. Peninsular soils are sedentary, meaning they are formed in situ, or directly from the decomposition of the underlying rocks. Because of this, they are generally coarse-grained, more mature, but less fertile. In contrast, extrapeninsular soils, like those in the Indo-Gangetic Brahmaputra plains, are transported or azonal soils. They are formed by the depositional work of rivers and wind, making them very deep and highly fertile due to constant replenishment. The vast and diverse landscape of India gives rise to a wide variety of soil types. We can categorize them into 8 major soil groups. These are alluvial soils, black soils, red soils, laterite and lateritic soils, forest and mountain soils, arid and desert soils, saline and alkaline soils, and finally, peaty and marshy soils. We will examine the unique characteristics, chemical properties, and agricultural significance of each of these groups. Let's begin with alluvial soils, which form the largest soil group in India, covering about 45.6% of the total area. These soils are primarily formed by silt deposited by the mighty Indo-Gangetic Brahmaputra rivers. Because of their recent origin, they are considered immature and have weak profiles. However, their loamy nature makes them highly porous, providing excellent drainage and favorable conditions for agriculture. Plus, recurrent floods constantly replenish these soils with fresh nutrients. Chemically, alluvial soils generally have a low proportion of nitrogen, but they contain adequate amounts of potash, phosphoric acid, and alkalis. They are widely distributed across the northern plains, the Narmada and Tapti valleys, and the eastern coastal deltas. Geologically, the alluvium of the Great Plain is divided into the newer Khadar and the older Bangar soils. Because they are mostly flat and respond incredibly well to irrigation, they yield splendid crops of rice, wheat, sugarcane, cotton, and jute. Next, we have black soils. The parent material for most black soil in India is the volcanic rock formed in the Deccan Plateau, specifically fissure volcanic rock. A defining characteristic of typical black soil is that it is highly argillaceous, meaning it contains a large clay factor of 62% or more. This gives it an incredible ability to retain moisture. In summer, the soil shrinks and forms deep cracks, which naturally oxygenates the lower layers. But in the rainy season, it swells and gets very sticky, making plowing quite a demanding task. You might wonder where the distinct black color comes from. It is due to the presence of a small proportion of titaniferous magnetite, or black constituents from the parent rock. Chemically, these soils comprise about 10% alumina, 10% iron oxide, and adequate lime and magnesium, though they are low in nitrogen and humus. Distributed across Maharashtra, Madhya Pradesh, Gujarat, and parts of the south, these are famously known as black cotton soils, or regur, because they are exceptionally suited for growing cotton, along with wheat, jar, and tobacco. Let's look at how this topic is tested. In the 2021 UPSC exam, a question asked, "The black cotton soil of India has been formed due to the weathering of what?" The correct answer is fissure volcanic rock. These are igneous rocks formed from the cooling and solidification of lava flows that erupted from cracks or fissures in the Earth's crust. The Deccan Taps, a vast region of volcanic rock formations, are the primary source of this parent material. Moving on to red soils, which form another massive soil group. Their main parent rocks are crystalline and metamorphic rocks like acid granites, gneisses, and quartzites. The texture of red soils mostly consists of loams. On the uplands, they tend to be poor, gravelly, and porous, but in the lower valleys, they become rich, deep, and fertile. Chemically, they are acidic due to their parent rocks and are generally poor in lime, nitrogen, and humus, though they are fairly rich in potash. The signature reddish color of these soils is due to the wide diffusion of iron oxide rather than a high percentage of it. Red soils mostly occur in regions of low rainfall, occupying about 10.6% of India's total area. They cover almost the entirety of Tamil Nadu, as well as parts of Karnataka, Maharashtra, Odisha, and the Chota Nagpur Plateau. Because they are loamy, they cannot retain water like black soils, but with proper fertilizers and irrigation, they give good yields of cotton, wheat, rice, and pulses. This brings us to a 2010 UPSC question, which asked, when you travel to certain parts of India, you will notice red soil. What is the main reason for this color? The correct answer is the presence of ferric oxide. Ferric oxide is a chemical compound formed by iron in its trivalent state and oxygen. It has a distinct reddish-brown color, and its wide diffusion through the soil profile is what gives red soil its characteristic appearance. Now, let's discuss laterite soils. These are mostly the end products of intense weathering, formed under conditions of high temperature and heavy rainfall, with alternating wet and dry periods. The heavy rainfall promotes severe leaching, where nutrients, lime, and silica are washed away by water. What is left behind is a soil rich in oxides of iron and aluminum compounds, like bauxite. The word laterite actually means brick in Latin, which is fitting because these soils harden greatly when they lose moisture. Laterite soils are found on the summits of the western and eastern Ghats, the Rajmahal Hills, and the Malwa Plateau. Because of intensive leaching, they lack natural fertility. However, when properly manured and irrigated, they support valuable plantation crops like tea, coffee, and rubber. Economically, they provide highly durable building material, since they can be cut into cakes that harden like iron. Interestingly, as noted in a 2013 UPSC question, crops like tapioca and cashew nuts grow well here because their deep roots can access moisture and tolerate the acidic, low-nutrient conditions. Let's shift our altitude and look at forest or mountain soils. Covering about 8.67% of India's land area, these are heterogeneous soils found on forested hill slopes, particularly in the Himalayan valleys and the Ghats. Their formation is heavily governed by the deposition of organic matter derived from the forests, making them very rich in humus. However, they are deficient in potash, phosphorus, and lime, so they require a good deal of fertilizers. They are perfect for plantations in the peninsula and for temperate fruits and wheat in the Himalayas. In stark contrast, we have arid or desert soils, found in the dry regions of Rajasthan, Punjab, and Haryana. These soils consist of 90 to 95% wind-blown aeolian sand and very little clay. Chemically, they are poor in organic matter, but surprisingly high in phosphates. The calcium content actually increases downwards into the subsoil. While nitrogen is originally low, some is available as nitrates. If proper irrigation is provided, these phosphates and nitrates make the soil fertile enough to grow drought-resistant and salt-tolerant crops like barley, millets, and maize. A major issue in certain areas is the development of saline or alkaline soils, where the topsoil becomes saturated with sodium, magnesium, and calcium salts. This happens when undecomposed rock fragments weather and release salts. In places with poor drainage, stagnant water evaporates and leaves these salt deposits behind. Furthermore, in regions with a high subsoil water table, evaporation during the dry season pulls injurious salts upward from below through a process called capillary action, rendering the soil completely unfit for agriculture. To truly understand how salts move upward against gravity, we need to look at the physics of capillary action and surface tension. Surface tension is the elastic tendency of liquids to acquire the least surface area possible. It's what allows denser insects like water striders to float, and it causes a water drop to form a hemisphere. This same surface tension drives capillary action, enabling water, and the dissolved salts it carries, to flow upward through the narrow spaces in the soil. These saline and alkaline soils occupied about 68,000 square kilometers in India. Inland, they are often the unfortunate side effect of improper or excess irrigation in canal-fed areas of Punjab, Haryana, and Uttar Pradesh. Along the coasts, the problem is caused by the sea. In Gujarat, sea tides carry salt-laden deposits into estuaries, while in coastal Andhra Pradesh and Tamil Nadu, storm surges from cyclones push saline seawater inland, infiltrating the soil and degrading vast agricultural tracts. Finally, we have peaty or marshy soils. These develop in the most humid regions, where there is a massive accumulation of organic matter and soluble salts. They are characteristically black, heavy, and highly acidic. You will find them in places like the Alappuzha district of Kerala, the Sundarbans of West Bengal, and coastal Odisha. Because they are located in low-lying, humid areas, most peaty soils are completely underwater during the rainy season. However, as soon as the rains cease, they are immediately put under paddy cultivation. Understanding these diverse soil profiles sets the perfect stage for examining the specific conservation challenges they face, which we will dive into next. Let's look at the intricate interactions that actually form soil over millennia. The properties of any soil depend heavily on 5 major factors: climate, parent material, topography, time, and organisms. These elements drive the geological and biological processes that eventually give us the specific soil properties we see today. Temperature and rainfall are arguably the most critical factors in soil formation. They determine how effectively the parent rock weathers, how much water percolates through the ground, and what kind of microorganisms can survive there. Interestingly, 2 different parent rocks can develop into the exact same soil if the climate is identical. Conversely, the same parent material can produce vastly different soils under different climatic conditions. Let's look at some examples from India. Crystalline granites will produce reddish, clayey laterite soils in moist monsoonal regions, but in drier areas, they form non-laterite soils. In parts of Tamil Nadu, the combination of hot summers and low rainfall results in black soil, regardless of what the underlying rock is. And in the arid climate of Rajasthan, both granite and sandstone weather down into the exact same sandy soil. In arid and semi-arid regions, evaporation exceeds precipitation. With little vegetation, the soil lacks humus, making it light in color. These soils accumulate lime and are known as pedocal soils, meaning they are rich in calcium carbonate but low in organic matter. On the other end of the spectrum, in the cold climates of the Himalayan region, plant decay is incredibly slow, which leads to the formation of highly acidic soils. What happens in areas with heavy rainfall and high temperatures? During torrential rains, the upper soil is washed and materials are leached down into deeper horizons. Then, during the dry summer, evaporation takes over. Through capillary action, iron and aluminum oxides are drawn back up to the surface, giving the soil a distinct red color. The blazing sun then bakes this topsoil so hard it resembles a brick. In fact, the word lateritic literally means brick. Topography or relief is another massive factor. On steep slopes like hilly regions or plateau edges, soil erosion is rampant. This constant washing away of materials severely hinders soil formation, leaving barren slopes like the Chambal ravines or the higher, deforested reaches of the Himalayas. However, in areas of low relief or gentle slopes like the Indo-Gangetic Plain, materials are deposited rather than eroded, allowing deep, rich soil layers to build up over time. Next is the parent material, the actual rocks from which the soils are formed. This base material usually dictates the soil's color, mineral composition, and texture, though intense climatic weathering can sometimes alter these physical properties. Surface rocks weather into fine grains, providing the foundation. In India, parent materials are broadly categorized into 6 types, ranging from ancient crystalline rocks to recent deposits. The first category includes the ancient crystalline and metamorphic rocks. These are the oldest rocks, dating back to the Precambrian era, about 4 billion years ago, forming the basement complex of peninsular India. They are primarily granites, gneisses, and schists. Because they are rich in ferromagnetic materials, they weather down to form expansive red soils, getting their signature color from the presence of iron oxide. Then we have the Kadapa and Vindian rocks. These are massive, ancient sedimentary rock formations that can be up to 4,000 meters thick. When these rocks weather, they produce calcareous soils, which are rich in calcium carbonate, as well as argillaceous or clay-heavy soils. Unlike the crystalline rocks, these are mostly devoid of metalliferous minerals. The third type is the Gondwana rocks. These are also sedimentary, but they are much younger than the Cuttapah and Vindian formations. Because they haven't been subjected to as much geological time, weathering of Gondwana rocks gives rise to comparatively less mature soils. These soils generally have lower fertility, though they maintain a fairly uniform character wherever they are found. The Deccan basalts have a dramatic origin. A massive volcanic outburst over peninsular India created the Deccan Traps, covering 1 million square kilometers in basaltic lava. These basalts are packed with titanium, magnetite, aluminum, and magnesium. When they weather, they create a dark, incredibly fertile soil with a high moisture holding capacity. You probably know this famous earth as Rager, or black cotton soil. Finally, we have the Tertiary and Mesozoic sedimentary rocks, primarily found in extrapeninsular India, which includes the northern plains and the Himalayas. These younger rocks weather into immature alluvial soils, characterized by high porosity. Because these soils are often transported by rivers over long distances, they actually bear very little relation to their original parent rocks. Let's shift to the biological side, natural vegetation and organisms. Vegetation reflects the combined effects of relief and climate, and it heavily influences soil development. Densely forested areas contain some of the best soils in India because decayed leaf material adds humus. Humus is a dark organic matter from decayed plants and bugs. It acts as a natural fertilizer, holding onto water and nutrients, making it the main ingredient in truly fertile soils. Because different soils have different levels of humus, clay, and sand, they are suited for different crops. Clayey and loamy soils are great for cereals like wheat and gram. Paddy requires soils rich in clay and organic matter with excellent water retention. Lentils and other pulses need loamy soils that drain water easily. And cotton thrives in sandy loam or loam, which drains well but also holds plenty of air for the roots. Now, if you were to dig a deep trench into the ground, you would see a vertical section of different layers, known as a soil profile. Each of these layers, called a horizon, runs parallel to the surface and differs in texture, color, depth, and chemical composition. Let's break down these horizons from the surface all the way down to the solid rock. At the very top is the O horizon, where O stands for organic. This layer is dominated by organic material rather than minerals. It consists of surface litter, undecomposed or partially decomposed things like leaves, pine needles, twigs, and moss. It also contains fully decomposed organic matter, which we just learned is called humus. Just below that is the A horizon, commonly known as the topsoil. Here, organic matter from the O horizon mixes with mineral matter. It is usually dark in color due to the high organic content, making it soft, porous, and great at retaining water. This is the layer rich in life, providing the essential nutrients that growing plants need. Over time, water can wash or alluviate iron, clay, and aluminum out of this layer. When that depletion from the A horizon is pronounced, a distinct lighter-colored layer forms, called the E horizon. The E stands for eluviated. Eluviation is the movement of minerals and organic matter out of a soil horizon due to downward percolating water. Because it has been significantly leached of clay, iron, and aluminum, what gets left behind is mostly resistant minerals like quartz, sand, and silt. So where do all those leached materials go? They end up in the B horizon, or the subsoil. This layer accumulates the iron, clay, aluminum, and organic compounds washed down from the A and E horizons, a process known as eluviation. Because of this accumulation, the B horizon has a much higher clay content, making it harder and more compact than the topsoil above it. Beneath the subsoil is the C horizon. This acts as a transition zone between the actual soil and the solid bedrock below. It is made up of small lumps of broken rocks with cracks, representing the weathered parent material. You won't find much organic matter down here. Instead, it's characterized by larger rock fragments and the accumulation of soluble inorganic compounds. Finally, we reach the R horizon, which stands for bedrock. Unlike the layers above, this is a continuous mass of hard, unweathered rock. While it's not technically soil, it is the ultimate foundation for soil development. It provides the original parent material, and its characteristics directly influence the drainage, texture, and mineral composition of the soil layers that slowly develop on top of it over millennia. To wrap up our discussion on soil, remember that soil formation is a complex dance between climate, parent material, topography, time, and organisms. Climate acts as the primary driver of weathering, while the parent rock provides the foundational minerals.
Over thousands of years, these forces create distinct vertical soil profiles, with each horizon playing a unique role in supporting the ecosystems above ground.